let's just go on to section 3 then. Field axioms. Field axioms. Okay. So, this is basically some sort of, so let me say it this way, mathematicians like to take, a naturally arisen construction and describe its essence in a minimal way. Okay, so for example, suppose we consider the real line. Okay, suppose we consider the real line with your standard plus and your standard multiplication. Okay. The real, these properties satisfy certain laws, right? So we notice. So consider this triplet: the real numbers with the plus and the multiplication, and we notice that certain rules are satisfied. One, you have that if you add two numbers together and you add a third to it, it's the same thing as if you add the second pair of numbers first. Add the first thing onto the sum of the second two numbers, right? The associative property, right? Associative property. Okay. There are a bunch of other properties that you notice when you're a kid, maybe. A plus B is the same thing as B plus A, right? These days I'm trying to teach my son, about adding, and I say like, okay, Taka, what is 2 plus 3? You count, he'll say 5, and then I'll say, what's 3 plus 2? And he says, Dad, it's the same thing. It's the same thing. I think I started teaching my daughter a little addition before I started teaching my son. That is, she was younger when I started teaching her. And when I started teaching her, I'd say, what's 2 plus 3? And she'd figure it out. She'd say 5. I'd say, what's 3 plus 2? And then she'd count again. She'd say it's 5. Right. So the commutative property wasn't obvious to her. Only after I did this, many times did she start to realize, oh, it actually works out the same way no matter what order. But I think my son, being a little bit older than she was, has caught on already, and he just laughs. Dad, it's the same thing. Okay. So commutative property. I haven't tried the associative property on it yet, though. Commutative property. Number 3, there's this thing called the identity. There's the additive. So there exists an element called 0, such that 0 plus A equals A for all A in R. Right? There's this thing called the additive identity. And number 4, for each A in R, there exists this thing called negative A in R, such that if you add A with negative A, you get to the additive identity. Okay. And there exists something called an additive inverse. So this is like a formalization of stuff that children start to recognize about the real numbers. Okay. And those are all having to do with addition, right? There are similar ones having to do with multiplication, right? A times B times C is the same thing as A times B times A times the product of B and C, right? So A, B, and C are. There's an axiom there's the commutative. There exists a multiplicative identity, right? Exists what's called a multiplicative identity, right? This thing 1, this thing called 1 in R, such that 1 times A is A for all A in R. Right? There exists a multiplicative identity. There exists for all A in R but excluding 0, there exists this thing called A inverse. Right? There exists a multiplicative inverse such that A times its multiplicative inverse gives you the multiplicative identity. Okay. So there are these things. And then there's this one property, one axiom, one property that combines both of them. It's the distributive property, right? That B times, A times C plus C is AB plus AC. Distributive. Okay. Okay, so these things are called the field. These things actually are called, so you have R, right? And R has an addition, has two binary operations, plus and multiplication. And those operations satisfy these rules, right? Okay, these things are called, field axioms. Field axioms. Okay. So any triplet of a set and some multiplication and some addition that satisfy all the above axioms is called a field. On a field. Okay. Okay. So who can give me some other examples of fields? Who can give me an example of a field? Are there other fields? Is R the only field you know? Is Q a field? Let's think. Does its addition satisfy the associative property? Yeah. Commutative? Yeah. Is there a 0? Yeah. Are there additive inverses? Yeah. Right. Does the multiplication do all these things? Right? There's a 1, there are inverses for everybody, right? And the distributive property works. Okay, so yeah, Q is a field, right? So for example, Q with its standard addition and multiplication, that's a field. Any other fields that people can think of? Was Z a field? No, right? No, right? Because what axiom does it fail?
The multiplicative inverse.
Right. There's no multiplicative. A lot of there are elements of Z that have no multiplicative inverses. Right. There are some that do have inverses, but not everybody. Okay. So Z plus this is a field. This is not. Right. What about the collection of n by n matrices? Is that a field? Matrices, so you have, say, square matrices with their matrix addition and matrix multiplication. Is that a field? Okay.
Yeah, because you have the identity matrix, and then you can find the inverse.
Can you always find, does everybody have an inverse?
Oh.
Right, so you have to have, for everybody in your field, there'd have to be somebody that you can multiply it by and get to the multiplicative identity. Okay.
Doesn't sometimes AB not equal BA?
That's right. So do we have commutative property? No, actually. Right? So it's not commutative either. Right? So not a field. Right? Not a field. Not a field. What if I look at, say, Z mod 3? Z mod 3. So that is, if I have, do you understand what I mean by Z mod 3? Does everyone understand? Z mod 3 is just the elements 0, 1, 2, and when you add and multiply, you take it modulo 3. So for example, if I take 2 plus 2, that's going to be equal to 1 mod 3. Right? So 2 plus 2 is 4, but you subtract multiples of 3 until you get back into this set. Okay, so 2 plus 2 is 4, but in this world, 2 plus 2 is 1. Okay, 2 plus 2 is 1. Okay, or like 2 times 2. 2 times 2 is 1 mod 3. Right? Okay, so is this a field? Does everybody, the addition, these associative, commutative, blah, 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 additive identity, does everybody have an additive inverse? Can you get to 0? Can everybody get to 0? What's the additive inverse of 1? How do I get to 0 from 1? Yeah, 2 to it, I get to 0. If I have 2, I have 1 to it, I get to 0. Right? Everybody has additive inverses. Does everyone have multiplicative inverses? Right? If I want to get to 1, well, I multiply by 1, I have 1. If I want to get to 1 from 2, what's its multiplicative inverse? We said it. It's 2, right? 2 times 2 is 1, right? 2 times 2 is 1 in this system, right? So yeah, it looks like this is a field, right? In fact, this is a field. What about Z mod 4? Z mod 4Z plus dot. Is that a field? Who will figure it out first? Yes or no? You look like you have an answer.
I think no.
You think no because?
It doesn't have like a multiplicative inverse.
That's right. For example, 2, right? If I want 2 and I'm trying to get to 1, well, 2 times 1 is 2. 2 times 2 is 0, right? 2 times 3 is 2 again, right? And that's it, right? If I want 2 times 0 is of course 0, right? So there's no way of getting to 1 for that guy. There's no inverse for the number 2, right? Okay, not a field. And so you see, for example, if I have z over nz, and n is a composite number, right? If n is a non-prime number, then that's not going to be a field, right? Not going to be a field. Yeah.
Can you prove that? Can you prove that?
Yeah, right. Because I'll let you prove it. Right? If n is a composite number, right? Suppose n is some composite number, p1 times p2. Okay. Well then, not right now. Okay. Let's. You wait. If you wait for 5 minutes, 10 minutes, then we'll prove it. Yeah. Yeah. But yeah. Yeah, so I guess, oh, well, no, we can do it right now, right? Because, oh, no, forget it. wait for a few minutes, then we'll get to it. Yeah. Okay. So these are what are called the field axioms, right? You take R or you take Q, and you say, oh look, both of these things have similar properties. They satisfy all these things. Maybe this is what we want to take as our definition of this mathematical construction. And you might ask, why don't we include some other basic properties of Q and R? Why don't we include, for example, cancellation, right? That A plus C, if A plus C equals B plus C, then A equals B. Why don't we include cancellation? Well, the reason is that it's a consequence of our axioms. We don't need to throw it in because it would be redundant. That property already follows once you assume the field axioms. So there's a bunch of basic properties that just follow. So consequential properties. Right. So there's so let F be any field, then for A and B and F, you have a bunch of properties that follow. One is that cancellation, right? A plus B equals B plus C implies that A must be equal to B. 2, A times 0 has to be 0. 3, negative A times B. So the multiplicative inverse times B is the same thing as the multiplicative inverse of AB. 4, negative A times negative B. The multiplicative inverse of A times the multiplicative inverse of B is actually just AB. 5, if AC equals BC and C is non-zero, then A equals B. So cancellation for multiplication. And 6, if AB equals 0, then A equals 0 or B equals 0. Okay. Okay, so there's this bunch of properties that just follows from the axioms. Okay, so you don't need to. You might think, why didn't we include these guys in our list? Well, they follow from our list, so we don't need to. It'd be a waste of ink to include them. Okay, it would be sloppy to include them. Okay, and you see that this last one actually relates this question. Right? How do you show that if you have z mod some composite number times z, how do you show that that's not a field? Well, if it were a field, then getting 0 would force one of your two factors to be 0, right? But in this world, P1 times P2 is 0, and neither one is 0, right? So that tells you that this is not a field. If it were a field, there'd be no way to get 0 except by having one of these factors being 0. Okay, so in a field, what we say is that there's no there are no zero divisors. Okay, there are no zero divisors. But you see in this thing here, P mod NZ, where n is some composite, there actually are zero divisors, so it's not a field. Okay. Okay. So the proof of these facts is not the most exciting thing. It's basically just like using the basic axioms and let me show you some examples. We'll do a couple, and then we're going to stop. We'll move on to something else because it's not exciting. So let's prove the first one, right? So say that A plus C equals B plus C, right? And you want to show that A equals B. Right? So you want to show A equals B. So say, okay, well, just by, this is the same thing as that, so I'm going to add the same thing to both sides. This plus this equals this plus this. That's just, you're adding the same thing to the same thing. So addition, this is sort of like by the addition is well defined. If you want to explain why that actually happens. Okay, and then you say, and that implies that by associativity, by associativity, so that was A1. Right. And then we get A plus 0 plus B plus 0 by A3. Was it A3? It was A4, I think. Right. Additive. Let me just write what these things are. Associativity. This is the definition of additive inverse. Right. And then that means that the left-hand side is equal to A and the right-hand side is equal to A because 0 is the additive inverse. Okay. Any question, Ria?
No.
No? Okay, good. Any questions? Okay, so I'll let you try one. Do number 2. Show me that A times 0 equals 0. Using the basic axioms. I think there are a couple ways to do it. Let me just write down the beginning of the way they have in the book. They say, well, look, A times 0 is the same thing as A times 0 plus 0. Okay, that's how they start off their proof. Okay, talk to somebody nearby and say what you're thinking.
That if you did, like if you set 0 equal to plus negative b, and then you could like somehow keep it out that
Okay, would somebody like to say? I should say that these sorts of proofs are, the worst, sort of most awful, uninteresting sort of proofs. But anyway, I made you do one, so I let you. Would anybody like to say how they did it? No? That's all right. Maybe it's just too awful. Oh yeah, Katie, thank you.
I didn't do it the way you suggested.
Okay, yeah, go ahead.
I wanted to
Yeah.
see if you could correct what I did. I said A times then in parentheses B plus negative B.
A times B plus negative B.
Can we assume that B plus negative B is 0?
Sure. That was one of the properties, right? That if you add the additive inverse to this thing, then you get 0. So you're saying that A times 0 is the same thing as this?
Mm-hmm.
Okay. Yeah.
And then I distributed so there's AB plus or then minus AB.
Okay. So
Plus A times negative.
plus A times negative B.
Sorry.
Yeah. So I'm not gonna. Let's not. I mean, it's true. What you said is true, but we haven't proven it yet. So.
Okay.
You see what's
Yeah.
awful. Yeah. Oh, yeah. You see.
Yeah, so that is
Okay. Do you go on from there or?
oh, and then I did A times B plus or minus AB, but we
Okay. Yeah. No, let's let's go ahead and just assume that this is the same thing as plus negative AB, negative AB.
And then by additive inverse, but I don't know if you can say it.
Okay. So you see that you're really using these two facts, right? So you could say that if we had proven these two things, then that would be one way to do it. But in fact, I think we're going to use this fact to prove the latter facts. So you see what's sort of really irritating about this, that you're not allowed to assume things that seem completely obvious. But Mia, you look like you want to say something. Yeah. Okay. So let me just write down. Let me write down the book's proof, and let's get out of here as quickly as possible and move on to the next step. So the book, they say, okay, well, look, this is the same thing as A times 0 plus B plus A times 0, right? By distributed property, right? So we're only using the basic properties, the additive identity. Here we're using we're distributing, right? And then they say, okay, well then, in that case, 0. If this is equal to that, then 0 plus A times 0 equals A times 0 plus A times 0, right? Because you can add 0 onto anything without changing it, right? Again, additive identity, right? And then we say, well then, now let's use part 1, right? We have cancellation from part 1, so let's cancel off one of these things, and we get that 0 is equal to A times 0 by part 1. Okay, and so you see that A times 0 is 0. Yeah. In whatever field you have, A times 0 is going to be 0. Okay. So let me just cover the rest of them by saying etc. Okay. Next idea, order fields. Okay. because R is not just a field. R also has the sense of bigger, bigger than and less than, right? Greater than and less than, right? Okay. So let me give you this. This is a little bit different from what's written in the book, but it's basically the same thing. So given a set S with we call a binary relation less than or equal to an order or a total order if it satisfies three properties. One, given any A and B and S, either A is less than or equal to B, or B is less than or equal to A. Okay. It could be both, but at least one of these things has to be true. You can always, given any two elements, they can be compared to each other. Okay. So this property is called totality, right? The relation can be applied to any couple, any pair of elements. Number two, if A is less than or equal to B, and B is less than or equal to A, that forces the things to be equal to each other. It's called anti-symmetry. Number three, third property, if A is less than or equal to B, B is less than or equal to C, then A must be less than or equal to C, and this property is called transitivity. Okay, so just for example, right, so R with the standard less than or equal to, that is a set with a total order. Okay, so I should say blah blah blah, and we call S with this order an ordered set. So this is an ordered set. Okay. If you have the Oxford English Dictionary with the lexicographical order, right, then that's an ordered set, right, is also an ordered set, right? And you say, which one is before is less than the one that comes after, less than or equal to the one that comes after, right? So you can compare any two words, right? If two words are, less than or equal to each other, then they're the same word. If one word is before another and that one is before another, then certainly the first word is before the last word, right? So any dictionary with the lexicographical order is an ordered set. If I take the complex numbers, can anyone think of an order on the complex numbers? A way of ordering the complex numbers? Right? Complex numbers, right? Things that look like A plus BI, A and B are real numbers. There's a funny way of putting an order on it.
Would be A squared plus B squared. I mean, this is from motion.
A squared plus B squared. Okay, so you could say, well, let's look at the size of it, maybe. Let's look at the modulus, the size of the guy. But then, is it true that can you compare all elements? For example, if suppose you have two complex numbers and they're both the same distance, right? Then you have trouble. right? Because they're not. Which one is bigger, right? So one way is to use the lexicographical order. So you say like A. So you use the lexicographical order. In fact, I don't know any other way, but you can use the lexicographical order, right? So you say, 1 plus 2i is smaller than 1 plus 3i, right? You just compare. You say, well, this is my first letter. This is my first letter. They have the same first letter. I go to the second letter. Oh, 2 is less than 3, so this one is less than that one. Okay. Or if I have, 0 plus 2i, that's going to be less than. That's going to be less than 1 plus negative 5i. Right? Because I look at the first letter and I say, oh, look, this guy's first letter is less than that guy's first letter. So you can compare it just like as if they were words. Okay. Here's a non-example. If we look at R2 with the subset ordering, right? What's wrong with that? Why is that not an ordered set? So not an ordered set. So I'm not R2, but subsets of R2 with set inclusion as the order, right? So if you have set A is a subset of B, and set B is a subset of A, then certainly the two sets are equal to each other. Where does this fail? Property. Who's talking? Somebody's talking. Mia, was it you? No? Oh, Pam, yes.
I was just saying that is not an ordered set because would look at it as the negative numbers?
So the set is, you have the plane, and you look at all subsets. Here's a subset, here's another subset, here's another subset, here's another subset, say, right? And we say that D, this guy is contained in that guy, so I say that D is less than or equal to C. This guy is contained in that guy, right? But you see the problem, Mia, yeah.
That some of the subsets don't contain any of the same elements.
Say it again?
Some of the subsets, like A and B, don't contain any of the same elements.
Yeah. So how do you compare them, right? So we don't have totality, right? We can't compare them, right? We can't say, is A less than or equal to B? No, right? Is B less than or equal to A? No, right? So we don't have totality, although we do have the latter two properties, right? We do have antisymmetry and we do have transitivity. Okay. So that's the notion of an ordered set. And then the notion that's more relevant to us is the following. Given a field F with an order, right? So you have a field and it has an order. You have this field. You have an ordered set that's also a field. Okay. If A less than B forces A plus C to be less than B plus C, and if whenever A plus B, A is less than or equal to C, and C is greater than or equal to 0, you have AC less than or equal to BC, then we call this ordered set, this field with an ordering on it, an ordered field. Okay, so it's a field with an order, right? It's a field with an order that satisfies its properties, right? And further, that ordering interacts well with the multiplication and the addition of the field. Okay, so it's not just a field with an ordering on it. Okay, it's not just a field with an ordering on it. It's a field with an ordering that interacts well with the binary operations. Okay, so to make this clear, R with the standard ordering is an ordered field. C actually cannot be made into an ordered field. It's actually impossible. And I think that might be one of your homework assignments to show that it is impossible. And so you might say, well, what are you talking about? C is a field, and C had this lexicographical order on it. But the lexicographical order doesn't work well with the doesn't work well with the addition and the multiplication. Okay, so it's not just a field with an order. It's a field with an order that behaves well with the binary operations of the field. Okay. Now, just like we had a bunch of consequences for the fields, there actually are also consequential properties of ordered fields. If you have an ordered field, right, if f less than is an ordered field, then a bunch of properties follow. First, whenever a is less than or equal to b, you have negative b less than or equal to negative a. Whenever you have a less than b, c less than or equal to 0, then bc is less than or equal to ac. So this is your the elementary, the bane of elementary school students, right? When you multiply by a negative number, you have to change the order. Right? You have to flip the sign, right? And even of like some first-year college students, I see them. They often forget to do this. Okay. Other things: if 0 is less than or equal to a, 0 is less than or equal to b, then 0 is less than or equal to a times b. Number 4, 0 is less than or equal to a squared for all a. Number 5, the one that seems to bother a lot of people, 0 is less than or equal to 1. Number 6, if 0 is less than a, then 0 is less than a inverse. And number 7, if 0 is less than a, that's less than b, then the inverses are in the opposite order. Okay, and we never explain what we mean by less than. Of course, less than means a less than b means that a is less than or equal to b, and a is not equal to b. Okay, so these are all things that are sort of along the lines of they seem like they ought to be true, and in fact they turn out to be true in the most boring way. Okay. So I'm going to end this class with with two extremely boring statements, extremely boring proofs. Okay, or maybe to make it more interesting, I should make you do it. So let's prove number one. The claim is that if A is less than or equal to B, then negative B is less than or equal to negative A. Okay. Okay. So try and prove it using, using our basic facts, using our, what the definition of an ordered field, right? We want to show that if this happens, then that happens. Right? So I'm just going to give it to you. Like, how do we get it? Suppose we start here. How do we get to here?
Can you substitute what A less than or equal to B translates to, and then subtract C? Does that make sense?
I'm not sure what you mean by substitute.
So for the first bullet point, we said that A is less than or equal to B translates to A plus C is less than or equal to B plus C.
Implies. It's not a translation. It makes A plus C less than B plus C. Yeah.
Can you use that though?
Sure, we can use it.
So you just copy that over and then subtract C for both sides?
What is C?
What is C?
Yeah. What are you using as C? So for any A, B, and C, it's true that if A is less than B, then you can add a C to both sides, and the inequality is preserved. Mia, sorry, in the interest of time, let me just.
Just going off what she said.
Yeah.
You add C, but where C is equal to negative A plus negative B.
Great. So you say, well, by property one, right, by property one from over there, we know that A plus negative A plus negative B is less than or equal to B plus negative A plus negative B. Right. Yeah.
And then you just use associativity in
Yeah. And then by associativity, we get that this plus negative B is less than or equal to this, and commutativity, I guess, negative A plus B, right? And then use the additive inverse property, which I think will say 4. You get 0 plus negative B is less than or equal to negative A plus 0. A3 implies that this is this. Good. Okay. And then the rest follow in some other ways. I'll just write it somewhere again. Okay, that's it for today. Next class, we will get into section 4. Section 4, finally, I think is something that is where we start talking about what's different, what's special about R. Okay, and it's this thing called the completeness axiom. R has this condition called completeness, or also called the least upper bound property, and it may take some thought to really understand. Okay, so the next section is a little bit trickier than all previous sections.